This is an example of an optimization problem on an open interval. So in this case, we don't have endpoints. We'll be looking for our absolute max or absolute min at a critical value, and then to confirm, in this case, we're looking for a min, and to confirm that's an absolute min, we'll have to look at the limit as x approaches the open endpoints. So we start with a closed cylinder, a cylindrical can that can hold 1 liter, which is the equivalent of 1,000 centimeters cubed. And the question is, what height and radius will minimize the material needed to make the can? If I'm looking for the amount of material, I'm looking for surface area. And so I want to minimize the surface area given a fixed volume. So I'd like to come up with my objective function. And in order to come up with my objective function, I want to just take the can and open it up. So if I have, in other words, here's my can, if you think of making a cylindrical can. And so when we think of the material made or used to make this, we'd have the top and bottom. And if we took the material used to make the sides of the can, if we open that up, it's actually going to be a rectangle. And so the area of each of the top and the bottom would be pi r squared. And when you think of the length of this rectangle, it's actually the circumference of the circle. If you took a can and sliced it up and opened it, the length of this rectangle is going to be the circumference of the circle, which would be 2 pi r, and then the height would just be h. So in order to come up with a formula for my objective function, it's going to be the surface area, or area, will equal 2 of the pi r squareds, because we have a top and a bottom, plus the area of the rectangular portion, which would be 2 pi r h. And we want to minimize this. Now we need a secondary equation so that we can eliminate a variable, and our secondary equation is that the volume is equal to pi r squared h, and actually pi r squared h is equal to 1,000 because we know what the volume is. I want to eliminate a variable, and if I could eliminate r or h. If I solve for r, I'm going to have to take the square root. So to keep this problem easier, I'm going to solve for h, and I'm going to say that h is equal to 1,000 divided by pi r squared. Now, my goal was to rewrite the objective function in terms of one variable, so I'm going to eliminate h. So I'll have a as a function of r. I'll have 2 pi r squared plus 2 pi r times the 1,000 over pi r squared, or 2 pi r squared plus 2,000 over r when I simplify. Now I'm not going to combine these into one fraction yet. I do think it's easier to take the derivative first and then combine them into one when you're trying to find your critical values. So I've started off, I've drawn my picture. I've stated my objective function, but it was in terms of two variables. I used my secondary equation, which was the fact that we knew that the volume was equal to 1,000, and the formula for the volume of a cylindrical can is pi r squared h. And then we solved for h, substituted that back in. Before I even take the derivative, I want to find the domain. And what I know is that I know that r I would state that r would have to be greater than or equal to 0. The radius could be, if it equaled 0, essentially I'd have a can that had no radius, or a 0 radius. But I can't have r equaling 0 because r is in the denominator, and we can't have 0 in the denominator. So I won't have an endpoint. I know that, or I won't have a closed endpoint to check. I also know that h, which is the height, that would have to be greater than or equal to 0, which means that 1,000 over pi r squared would have to be greater than or equal to 0, but it can never equal 0 because the numerator is 1,000. And I also know that this is always going to be positive. My domain is from 0 to infinity, so I have an open interval. Now from here, I will take the derivative to find my critical values. I know that if I'm going to have an absolute max or an absolute min, and again in this case I'm looking for a min, that it will occur at either endpoints or the critical value. Now since I have an open interval, it has to happen or occur at the critical value, and then I'll test my open endpoints. So I take my derivative, a prime of r equals 4 pi r minus, when I take the derivative of 2,000 over r, I'm going to get, it's negative 2,000 over r squared. And here's where I do believe it's easier to combine these into one. So if I multiply the 4 pi r by r squared over r squared, I get 4 pi r cubed minus 2,000 all over r. Now when I go to find my critical values, I know that one of them would be when the denominator equals 0, but that's not in the domain. My other critical value would be when the numerator is equal to 0, 4 pi r cubed minus 2,000 equals 0. That means r cubed would equal 500 divided by pi when I divide both sides by the 4 pi. And my r is going to be equal to the cube root of 500 over pi, which is approximately 5.419, and that would be centimeters. Now I know that at my critical value, if I only have one critical value, I know that it's got to be an absolute max or an absolute min. So we now want to confirm that the absolute min in fact does occur here, and we'll do that by looking at our endpoints. And in this case, again, we can't test our endpoints by plugging those values in the function because the function is not defined there. We can look at the end behavior by looking at a limit. So we're going to take the limit as r approaches 0, which is our left endpoint, and we'll take the limit as r approaches infinity, which is our right endpoint. And when we let r approach 0, the first term of this function goes to 0. The second term will go to infinity. So we have 0 plus infinity is infinity. The second limit is the limit as r approaches infinity, in which case the second term will go to 0 and the first term will approach infinity. And so our end behavior as we go to 0 and infinity is infinity. So we do in fact have an absolute min that occurs at the cube root of 500 over pi. To put the function in my calculator and find out what the absolute min is. So in my y1, I've got the original function, the 2 pi r squared plus 2,000 over r. Instead I'm using x instead for my r. And I'm just going to quit out of here and go to my home screen. I'm not going to graph it yet. I'm going to go to vars and yvars, and I just want to evaluate. I'm going to open the parentheses, Now I need to open the parentheses again because I want to take 500 divided by pi and raise it to the 1/3. You can do that, or there is a cube root button you can also use. I'm going to take 500 divided by pi, close the parentheses, raise that to the 1/3. If you do not have the latest version, you're going to need parentheses up in your exponent, and then I'm going to close that. And I'm going to hit enter. And so I get the absolute min is approximately 554. So I'd say the minimum surface area is approximately 554 centimeters squared, and it occurs when the radius is approximately 5.4. Now I still think it's a good idea to graph the function, and now that we know we believe that we know what the absolute min is, and we also know where it occurs, when we go to choose our window, we could go, let's say, from 0, maybe from 0 to 10 on the x, since my max is occurring at around 5. My y min, I could go from 0 to maybe 600 or 700, maybe a little bit, beyond. I want to go beyond the 550. I'm going to graph that. And there, if we trace on approximately 5.4, so I might not throw in the 19. You can see there that that is the minimum value of our function. We can zoom out on this if we want. If you want to look at your end behavior, so I hit zoom out, hit enter. And we can see now over here, the function itself, a of r, does have negative values in its domain, but we're talking about a physical domain here. So this portion of the graph is not suitable for our problem, right? The physical domain is from 0, not including it, but x is greater than 0 over here. And we can see that our minimum does in fact occur, and we can see it looks at our end behavior is going to infinity as x approaches 0 and as x approaches infinity.